Okay, great. Good morning, everyone. I had to modify the slides at the last moment to address few of the comments I have got on the mailing list. So the slides might not have come out very well. Please bear with me. So to start off with a couple of acknowledgements. Malvika and Dharmika are in my team. They helped me create the test cases to test this library. So thank you very much. And finally, thank you for the DPDK community for every comment out there. It was very important that we discussed those comments in detail. Okay, so what I want to do today is talk a little bit about the value that this patch is bringing out in terms of what's available out there already. So from that perspective, I would like to define few terms and parameters that affect memory reclamation. And then, what is the effect of these parameters? How does it affect reclaiming memory? And then I will talk a little bit about the requirements that I have been working with that apply for DPDK in particular. And then I'll go a little bit into the design, which talks about how I have addressed these requirements. Okay, good. So coming to the terms and parameters. Lockless algorithms are great. They provide you the scalability and determinism without requirement for any additional hardware. But they come up with their own problems. The problem is memory reclamation. It's not very straightforward to what we have learned in our college days, wherein you allocate memory and free memory when you don't want it. So what we have here is we have got reader threads that make use of the data structure. And each reader thread accesses a shared data structure. For example, here the red ones are the shared data structures. They are being written by the writers, and the readers are reading them. So those red spaces over there are the critical sections. And then you have the green spaces in between, where the readers don't access any shared data structure. And that we call as quiescent states. So now, you want to delete an entry from the data structure. So at that point, the delete comes along, but we cannot free the memory at that very point because, as you see, the reader threads might be using that entry that you want to delete. So you got to wait till the reader threads are done using that entry. So where is that place in time? So this is the place. This is the place in time where you can go ahead and free the memory associated with that entry. So this time gap between delete and free is the grace period. And it is very important for the writer to wait for this grace period to get over before he can go ahead and free the memory. So, three important points. One is critical section, quiescent state, and grace period. And we'll see how these parameters affect memory reclamation. Yes, you can have multiple deletes going on. There might be multiple writers. So grace period. So, as you can see here, in order to determine the grace period, the writer says, okay, start. He gives a start command to the readers, and then he starts polling. He starts polling for whether the readers are done or not. So what does that polling mean? It means that there are going to be memory excesses. Can we avoid that polling to reduce memory excesses? And then it also means that the writer is spending CPU cycles doing that polling. So essentially, continuous polling means increased memory access. And then, it can happen that the writer might not start the detection of the grace period immediately after delete. So what that means is your grace period is extended. So with the extended grace period, you are going to hold up your memory for a longer time. Because you said delete, but now you can't free it. So if you have a longer grace period, then you are going to hold up your memory for a longer time. So what that means is, during this in order to address the grace period, you got to have extra resources. For example, if you have got a hash table and you have got free entries, then in order to address the grace period, you need to have those extra entries. And the longer the grace period, you need more extra entries. So now, going to the critical section. So how does a smaller and versus bigger critical section affect memory reclamation? So here, you see that, in the readers, you have got smaller critical sections. So which is good from the perspective of keeping your grace period smaller. So the advantage is you get smaller grace periods, which means that you don't have to have too many additional resources. But the disadvantage is that the readers will spend more cycles reporting their quiescent state. So, on the data plane, we all worry about the number of CPU cycles that we spend. So that's one disadvantage in having smaller critical sections. Now, so what can we do with this? So we can merge critical sections and make them bigger, but that increases your grace period. So the advantage is you will spend less number of cycles on the readers, reporting your quiescent state. That's good. But the disadvantage is you have a larger grace period. What that means is you are going to poll for longer period, which equals to more memory accesses, and then you are spending more CPU cycles, and then there is, the extra amount of resources increases further. Okay, so now having understood these parameters, what are the requirements? So from my perspective, we need characteristics of large critical section and then smaller grace period. This is what we need to get the benefit of, to get the performance. So keeping that in mind, here are the few requirements that I have come up with. Can we reduce the number of CPU cycles required for grace period detection? And then that's because you have a larger critical section. Then can we reduce the polling during grace period so that you have less number of memory accesses and less amount of contention and all that? Can I have distributed and concurrent grace period detection? So what that means is I can have multiple writers who are doing grace period detection in parallel, and overall you reduce that duration. So that puts a requirement that we need a lock-free algorithm, because if you have the writers on the data plane, you don't want them to be blocking the other writers. The second one is don't enforce a programming model. You want to do bulk memory reclamation, that's fine, but don't say that, hey, you got to do it in a separate thread. That should be a decision that should be left to the application. If it wants to have a separate thread to do memory reclamation, that's good, it can do it. But if it wants to do inline in the writer threads, then that should be allowed. Then the third one I have here is the RTE event DQ burst. It supports blocking mode. What that means is worker threads can block for a longer duration. So we need very efficient, bother about me, or I'm going to report the status now, and I want to stop reporting the status now. These APIs need to be very efficient because they are going to be called for every while loop on the data plane. on the worker threads. So I think these are some of the requirements that I have been working with. So let's see what I have got in the design that satisfies this. So first of all, in the patch that I have put out, the list of readers is represented as a bitmap. So what this allows is it's very efficient, and it allows for lock-free and concurrent operations. And this is important because if you want to do these things in the data plane, you don't want to be blocking your worker threads. So the second thing I have done is I have split the quiescent state detection in 2 steps. So this allows me to run multiple concurrent quiescent state queries. So the first API that's provided here is the TQS start. So this API is lock-free. What that means is you can have writers on the data plane, multiple writers on the data plane, and all of them can call this API simultaneously and concurrently. And this allows for writer to start the grace period detection process without having to wait for the end of someone else's grace period, some other writer's grace period. They don't have to wait for each other. They can start their own process in parallel. So the other thing about this API is it just starts the process. It does not wait for the grace period to get over. So what that means is your writer thread has the choice of starting the process and then go and do some other work. So that has a couple of advantages. First thing is you are not wasting CPU cycles waiting for your grace period to get over. The second thing is you are not polling continuously. There's no more memory excesses because of continuous polling. So yeah, that's the last point there. So the second API is the TQS check. So again, this API is lock-free. You can run it concurrently. Multiple writers can call this simultaneously. And the advantage here is, if you called the start and you did some other work and come back and call this, there's a very likelihood that you have already completed your grace period. So most probably, in the first polling attempt, it says that yes, your grace period is over. So you are completely avoiding the memory accesses due to polling, as well as you are making use of the CPU cycles during that grace period. So this does not enforce any threading model for batching. You are free to create a parallel thread or an independent thread that does reclamation, or you can do it in line with the in the writer thread. Then I have the TQS register and unregister APIs. These are lock-free. So you get a packet from the event dev. Then you can say that, hey, I'm going to start reporting the status now. And then you are done processing. You are going to go into that blocking call again. You can say that, hey, I'm not going to report the status anymore. So these can be called from the worker threads. They are very efficient and lock-free again. So this is all the value that this library brings in when compared to the existing solution. So the code is out there. You can go take a look. But I really wanted to focus on the value that it's bringing in so that everybody is clear as to why this library is required in DPDK and how it is suitable for DPDK workloads. So good. So that's all I have. It is very simple, and there have been a lot of questions, a lot of concerns. So I'm here. Please feel free to ask any questions. And I feel we should look at the value that this brings in, and then we talk about whether we get into DPDK, and all those other things. I'm sorry? Yes, I kind of had to address the community comments. So I had a different set of slides, and I had to convert all of them. I had to change all of them. I kind of completed yesterday night, so hopefully I'll get them uploaded today. Okay, good. So thank you very much. I think we did some more testing, and there were a few issues found. We will address them in the next patch set, and we'll go from there. Thank you.